Model specification refers to the process of selecting the appropriate functional form and explanatory variables for a regression model. A correctly specified model includes all relevant variables, excludes irrelevant factors, and accurately reflects the economic relationship being analyzed. In investment applications, model specification is critical because inaccurate models can lead to biased forecasts, incorrect valuations, and poor investment decisions. Common objectives include explaining security returns, identifying risk factors, and forecasting economic variables. Analysts must rely on economic theory, prior research, and professional judgment when selecting independent variables to ensure the model captures the true drivers of the dependent variable while avoiding unnecessary complexity. One of the most significant challenges in model specification is misspecification error. Omitted variable bias occurs when an important explanatory variable is excluded from the model, causing coefficient estimates to absorb effects that belong to the missing variable. Measurement error arises when variables are inaccurately measured, while incorrect functional forms may fail to capture nonlinear relationships. Misspecification can produce biased and inconsistent coefficient estimates, misleading statistical significance tests, and poor predictive performance. Analysts should evaluate model assumptions carefully, review economic reasoning, and compare alternative specifications to minimize these risks. Proper specification is essential for generating reliable and meaningful regression results. Another important concern is heteroskedasticity, which occurs when the variance of regression errors is not constant across observations. Heteroskedasticity is common in financial data because firms, industries, or markets often exhibit different levels of volatility. Although coefficient estimates remain unbiased, standard errors become unreliable, leading to incorrect t-tests and confidence intervals. The Bruch-Pagan test is frequently used to detect heteroskedasticity. Analysts can address the problem through robust standard errors, variable transformations, or alternative estimation techniques. Recognizing heteroskedasticity is important because inaccurate statistical inference may cause analysts to incorrectly conclude that a variable is significant or insignificant when making investment decisions. Serial correlation and multicollinearity are additional specification issues that affect regression analysis. Serial correlation occurs when residuals are correlated across time periods, often in time series data, violating the assumption of independent errors. This can result in underestimated standard errors and overstated statistical significance. Multicollinearity occurs when independent variables are highly correlated with one another. While coefficient estimates remain unbiased, multicollinearity increases standard errors and makes it difficult to isolate the individual effect of each variable. Analysts should evaluate correlation structures, diagnostic statistics, and economic logic when interpreting results, particularly when multiple explanatory variables capture similar underlying economic information. Extensions of multiple regression allow analysts to model more complex relationships. One important extension is the use of qualitative, or dummy variables. Dummy variables take values of 0 or 1 to represent categories such as industry classifications, geographic regions, or company characteristics. Their coefficients measure the difference between a selected category and a reference group while holding other variables constant. For example, a biotechnology industry dummy can indicate whether biotechnology firms command higher valuation multiples than utility firms after controlling for other factors. Dummy variables enable analysts to incorporate qualitative information into quantitative models and improve explanatory power. Another major extension is logistic regression, which is used when the dependent variable is binary rather than continuous. Instead of predicting a numerical outcome, logistic regression estimates the probability that a specific event occurs, such as default, bankruptcy, credit downgrade, or earnings surprise. The model transforms probabilities into log odds, allowing estimated coefficients to describe how changes in explanatory variables affect the likelihood of the event. Model comparison often uses likelihood ratio tests, which follow a chi-square distribution. Logistic regression is widely used in investment management because many important decisions involve classifying outcomes rather than forecasting continuous values, making it a powerful complement to traditional multiple regression techniques.